So, welcome to the first afternoon workshop for mathematical analysis, 4 o'clock on Tuesdays. As I've just been mentioning before, this workshop is for everyone who can come to it. The 10 o'clock Tuesday workshop is only for people who can't come at 4 o'clock. And we're going to start today with a description of what the module's about, which will be about the first half of the session, maybe a bit more, and then we'll have a revision quiz to see how much you remember from last year. And the 5 handouts today, if anybody hasn't collected those, they should collect them at a suitable point. So I'll start by reminding you that you're supposed to be working 35 or 36 hours a week during term time. And so you do a quick calculation and you'll find out that you should be working 6 hours a week on this module. But there's only 3 content hours a week, so that leaves 3 hours when you should be working in your own time. And there's plenty of things you can do. There'll be loads of question sheets you can look at. There'll be the module lectures to look through and to think about, and then you can perhaps talk about it with friends, come and ask me questions, get further help from anybody who can give you help. And it's not a particularly easy module, so you should find good use for that time. So what's it all about? Well, we're following on from what you did last year, but we're going to introduce new concepts and a lot more rigor. Well, actually, you saw quite a lot about mathematical proof in analytical and computational foundations. So you saw quite a lot of proof, but you were told that you wouldn't need to reproduce most of those proofs in the exam. And that may have meant that you regarded those proofs as not that important since you weren't going to be examined on them. Actually, those proofs are rather interesting, and you might want to go back and look at them, because this module is going to be full of proofs, and this module, one of the aims of this module, in fact, is to get you used to the ideas of how to do proofs in mathematical analysis. So this module isn't just about learning things that are true, it's also about how they're true, how you know they're true, why certain things are true. And also I'm going to be giving you various optional extra sessions, which are actually available to all the second years, on why do we do proofs at all, and how do you do proofs in general. And that will be 3 special sessions, which you'll find listed in the list of workshops. If you look on the module information page, it tells you what the workshops are intended to be, and included in those are these 3 optional sessions on how and why we do proofs. Now you can't do that much in 3 hours, so this whole module is really about how and why you do proofs. And it's full of proofs which you're going to have to understand, which you're going to need to be able to produce if you asked for it in the exam. And some people take the approach that that means you've got to memorize 100 proofs. And that's not a very efficient way of doing things. In my view, what you need to do is understand how to do proofs in a standard way. You need to understand the main ideas and concepts of the module. And then most of the proofs write themselves, with a few exceptional tricks that you need to know. So I would have thought that if there is an element of memorization, it would be a very selected bit of memorization on those bits which aren't what you expected. But of course that's in the ideal world, because part of what you're learning this year is what's expected, and your instincts may not be tuned yet. So there's an awful lot of work to do to get good at understanding proofs and doing proofs, and also you have to put a lot of work in order to make studying this module efficient. If you try to minimize the amount of work on this module, you'll find that you probably end up doing more work and having to try and memorize lots of stuff that you don't quite understand, and then forgetting it straight away, and this is not necessarily a good use of your time. So last year, as I said, you did learn quite a lot about proof in analytical and computational foundations. In calculus, perhaps more of it was here's what is true, and less of it was probably here's proofs of why it's true. Though I think that there are some proofs in calculus. I don't know how many of those proofs you were asked to learn for the exam, And again, I don't know how seriously you will have regarded the proof element of calculus from last year. It's very different in this year. In all the pure modules, proofs, and from now on, in all the pure modules, with the possible exception of complex functions, which is slightly different in nature, but in all the other pure modules, proof is really crucial, and you're expected to be able to know proofs and to be able to do proofs for yourself. Prove, if you're given some fairly straightforward thing to prove, but that you've never seen before, how to prove it, you're expected to be able to work out the proof for yourself in the exam. Now we're going to look at loads of examples to help us, and there's going to be quite a few interesting concepts. Now the pure modules in second year, there's this module on mathematical analysis, then there's algebra and number theory, which is 30 credits and which includes algebra and number theory. And I would say that analysis, algebra and number theory are the three main types of pure mathematics you can do here, with some other elements of sort of graph theory, combinatorics. But mostly it's that our three big research groups and our three big teaching areas are mathematical analysis, number theory and algebra. The complex analysis part, complex functions, that's a bit of an outlier. As I said, there's not, proofs are available to you in complex functions, and you'll be told quite a lot of theory, but in complex functions, in spring semester, it's more of a methods module. It's a really beautiful lot of theory, but the emphasis is on how to use the theory to calculate certain integrals and get answers, and about the way certain kinds of functions behave. And so it's more of a methods module. It's actually closer in nature to calculus from first year, except that all of the theory is available to you if you're interested in it. So I do recommend it. The beautiful module is a very different kind of module from this one, or from algebra and number theory. So let me tell you something about why we do proofs and how we do proofs. And I'm not going to say much about this, but I just want to point out to you that sometimes you have to be careful. So there's why do we do proofs and there's how do we do proofs. And I'm going to address the first one just mildly now by pointing out that you have to be careful sometimes. So why do we do proofs? Well, sometimes you have to be careful. You don't always know as much as you think you do. So I'll give you the following example to do with Taylor series. And the question is, when is it true, or is it always true, that you can write f of x as equal to f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial times x squared, and so on. The wonders of modern technology. There are, of course, problems, but I wonder how many problems people can think of. So this isn't always true. Can anyone tell me one of the things that can go wrong when you're trying to write a function as a sum of its Taylor series? Anyone got any ideas? For example, can every function be differentiated? Are there some functions you can't differentiate? Does anyone know a function you can't differentiate? Yes? That's right. If you have a discontinuous function, you can't differentiate it, so you're in real trouble. So that's a good example. Discontinuous functions give you trouble. Now suppose though, yes?
Like a modular function.
Modulus function, yes, y equals mod x. So let me just point that one out. That's a very, so the first problem is it can be discontinuous, then you can't differentiate it, so it's hopeless. Even if it's continuous, you can have trouble. And so you could have the function y equals mod x. So you may not be able to differentiate. So let's remind ourselves what that looks like. So I'll do you a quick sketch of what y equals mod x looks like. So there's y equals mod x, except that I've missed the origin. It's just put a blob there. There you go. Y equals mod x has got this spike at the origin, and you can't differentiate that function there, even though it is continuous. Now, you could say sort of on average it looks like the derivative might be 0 at the origin. But even if you did do that, you're still going to run into trouble if you try to do a Taylor series for it. But actually you can't differentiate at the origin at all. So you can't do a Taylor series for that function, at least not naively using the usual formula for differentiation. And you can have functions with lots more spikes than that, and so you can have problems at all sorts of points. So this is not differentiable at the origin. But even if you can differentiate your function, you can still run into trouble. So what trouble can you get into? Well, let me remind you of another strange function that you met in first year, the function e to the minus 1 over x squared. So even if you can differentiate, let's consider the following function. So it's e to the minus 1 over x squared if x is not 0. And it's 0 if x equals 0. You can't actually divide e to the minus 1 over x squared directly when x equals 0, but if you have a sketch of what this function does near the origin, and I'll leave it to you to think about what this function does if you're away from the origin, when x gets very big, it's not a very interesting function. The strange behavior happens near the origin. And the way this function behaves near the origin is it's incredibly flat. So flat that it's very hard to draw it sensibly. And if you ask Maple to draw it, it'll look as if it comes in along the axis, no matter what scale you look at. Once it gets away from the origin, it starts to turn around and heads up towards 1. But I'm not worried about that. So that's y equals e to the minus 1 over x squared, or y equals f of x. Well, I'll call it y equals e to the minus 1 over x squared. And of course, there's that extra point where it's 0 at the origin. It's incredibly flat at the origin. It's so flat that not only is f of 0 0, but all of the derivatives of the function are 0 at the origin. Now, this is not actually very easy to prove. It's a tricky little exercise to check these details. But what you get is you've got f of 0 equals f prime of 0 equals f double prime of 0, and so on. They're all 0. That's a tricky exercise. And that means the Taylor series is not going to be very useful if you expand it about the origin, because all you'll get is 0. And 0 is not very much like this function. In fact, the only place where this function takes a value of 0 is at the origin. So the Taylor series gives you the wrong value everywhere except at the origin. And that's in spite of the fact that it's differentiable as often as you like. So in some senses, it's a really nice function. It's as smooth as you like. In other senses, it's a really horrible function because the derivatives at the origin don't help you to know much about the function away from the origin. What does that mean? What's the moral of that story? That you can't just assume that things that you're familiar with are actually true. If you wanted to know what's really going on, there's actually an error estimate you can find. If you take a few terms of the Taylor series, there's an error estimate. And in this case, the error estimate is as big as the whole function was in the first place. And so you haven't got anywhere. Whereas for other functions, the Taylor series, Taylor-Maclaurin series about the origin gives you exactly the right value. And that means that there must be some theory going on behind there that explains why it's true. Now, we're not going to be covering Taylor series, Taylor's theorem in detail in this module. We'll be doing other things that are perhaps slightly easier than that. But even so, we're going to see situations where things look obvious, but where you need to be careful. Are you dealing with continuous functions? Are you dealing with differentiable functions? Are you really sure that you've checked every case? Are there some nasty examples around where you've got to become more careful? Right. Now, what kind of thing can come up on examination questions? Well, there's material that I call bookwork. Maybe about half of each exam question, varying. Some of them less, some of them more. But on average, maybe about half of each exam question might be bookwork. Maybe even as high as 60%. It'll vary from question to question. And some questions will be not bookwork at all. What do I mean by bookwork? Bookwork is standard material we've covered in lectures, and which therefore you're expected to know. And then you may be asked to reproduce some of this in the exam. If you do it by memorization, then you're going to have an awful lot to memorize. But if you understand what's going on in the module, then you're less likely to have to memorize things completely, because you'll just be explaining what you already know, possibly even in your own words. But not everything will be bookwork. There's going to be other stuff that may come up in the exam. There could be stuff that comes from question sheet questions and solutions. Some of the stuff that turns up may be exactly the same as things that come up there. Or there may be slight modifications. I tend to value that sort of stuff a bit more highly than I value the bookwork. So you get slightly more marks per word that you write, if you could do those. I should say that the exam questions will not say on them, this is the bookwork bit, this bit comes from a question sheet, and this bit is completely unseen. You'll have to work that out for yourself. But when we send these things out to the external examiners to check how hard the exam papers are, because they do look at these papers to check whether they're too hard or whether they think the level's about right, then we do tell them which bits are book work, which bits come from question sheets, which bits are completely unseen, so that they're able to make an informed judgment as to whether we're setting an exam that's at an appropriate level. So there are various non-bookwork sections, and if you may come across something that looks similar to something you did before but isn't exactly the same, slight modification. Again, that's worth slightly more marks per word that you write, I would say, if it's similar in style but a bit different. And then there's the entirely unseen parts. And those, of course, are usually the hardest bits, something that's more significantly different from anything that you've seen exactly before. Again, I regard those as getting more credit per word you write because it's harder if you haven't seen it before. And there'll be some of those on the exam as well. There's usually, I can't guarantee what will be where. I'm not going to tell you which chapter is going to be examined in which question. I tend to move things around a little bit. So I will expect you to try to understand everything in the module. Otherwise, there may be some questions that you won't be able to attempt bits of. But generally, for more information about all this, if you look at the module information page, there's quite a lot there. I printed out the latest version of the module information page. If there are any modifications, I'll correct it online and let you know if there's any significant changes. That will do for the first half of this session, and we'll have a short break followed by a revision quiz.